The history of Brachistochrone problem. This problem is usually solved using calculus, but there was one mathematician trying to solve this problem using geometry, which was Galileo Galilei. His geometric argument was making different chords of a circle starting at A through B and proved ACB was quicker than a vertical plane. And from this, he inferred that the circle was the solution. This wasn't an optimal solution, but was still closed using a geometry. Later on, Johann Bernoulli, a mathematician in Switzerland, solved this problem using calculus. He was the one proposing this problem as well. He challenged the mathematicians, and there were only 5 mathematicians solving this problem. It was Leibniz, L'Hopital, Newton, Jacob, and Johann. These were the 5 mathematicians solving this problem.
The Brachistochrone problem is a simple problem that's easy to understand with an elegant solution and proof. The Brachistochrone or cycloid curve, as seen in figure 1, transports a point particle down a descent from A to B in the fastest possible time. The problem was initially solved by analyzing properties of light, as it always takes the quickest path, and was later further proved using differential calculus, geometry, and the conservation of energy. The curve finds the perfect compromise between converting gravitational potential energy into vertical kinetic energy early in the path, but also turns that vertical kinetic energy horizontally to reach the finish in an optimal time. Though the math behind the curve can seem daunting, especially to a first-year engineering student, the resulting solution is actually very simple. As seen in figure 2, the curve traced by a rolling circle is by definition the cycloid curve, which produces our fastest route. This curve is essential to our success creating a roller coaster drop that is as fast and as thrilling as possible.
Roller coaster theory versus practice. So first, when developing a roller coaster, you'll be working with theoretical models, simulations, and predictions, and you'll be making lots of simplifications. And from these, you'll be receiving exact values. And you can use these results to construct real models from which you can collect experimental data and get ranges of results representing the actual values for that system.
As we start to build and model a roller coaster, we must consider the fun factor that riders will experience. This includes the thrill and the feeling of fear and pleasure. So how will these two factors affect the development of these curves? Well, if we can decrease the time it takes for the roller coaster to accelerate, this will increase the thrill factor that riders will experience. In addition, if we add more loops and turns, this can increase the G-force that riders will experience, hence creating the sense of fear in addition to euphoria that riders will experience, and hence creating a more fun and enjoyable ride.
Let's talk about roller coaster safety. Roller coasters in Ontario are regulated by the TSSA, which is the Technical Standards and Safety Authority, and they have a 5-step plan for you to allow public access to your amusement device. The first step is receiving an operating license, and this is done by providing proof of a $2 million insurance policy and that you are or employ a licensed amusement device operator. Next, you will submit your technical dossier, and this includes specifications of the ride, the maintenance schedule, and the operating schedule of the ride. This and the design of your ride will be reviewed by TSSA engineers, and if it's safe and feasible, then they will send an inspector to visit the ride itself. They'll make sure that this is in accordance with all your documents, and if it is, then you will be issued your permit and a metal plaque, and this has your ride number and must be affixed to your ride and visible at all times. The TSSA also has standards for the operation of the device. So all electrical components must always be up to the Ontario Electrical Code, and any welding done on the ride must be overseen by a professional engineer. The maintenance of the ride must be done according to the manufacturer, and if they're not available, then a professional engineer can oversee this. There are fencing requirements for roller coasters, so the entrances and exits must be fenced off so that no one can accidentally board the ride. And an environmental analysis must be conducted throughout the lifetime of the ride about the setup of the ride, the teardown of the ride, and the operation of the ride. So switching a little bit to talking about choosing the safest path for the roller coaster. The most common injuries on roller coasters are brain and spinal injuries, and these are caused by acceleration of the head relative to the neck. So a study was done on one roller coaster, and you can see on this graph, this shows the acceleration of the riders throughout the ride, and that peak acceleration is where injuries are most likely to occur. And these are caused by the head accelerating relative to the neck. So one way to prevent this would be high back seats, so that if the ride accelerates quite quickly, you accelerate, like your whole body accelerates instead of your head kind of whipping back like that. Whereas if your seats were kind of lower, then your head and your neck could kind of whip like that, and that's not safe.
Problem definition would be in 3 main points. One is constraints, one is stakeholder, and one is scope. The main constraints would be financial feasibility, resource availability, weather conditioning, and 12 weeks timeline. In this timeline, we are now reaching week 5. And for stakeholders, we'll have Scary Ride Inc.'s Department of Mathematics and Statistics and the passengers. And for the scope, the focus is going to be on the drop portion of the ride. And we'll be achieving this using brachistochrone or cycloid curve. And we'll have 3 variations of the drop, which will be produced for Scary Ride Inc.'s.
By looking at our timeline, we can determine which tasks we've already completed and what tasks we need to focus on in the future. Some things that we have already done as a team include researching the history behind the calculus of the problem. We've also determined whether we're going to use wood or steel on the roller coaster. We've also considered the safety for riders, and we've determined which curves can be too harmful. We've also researched what fun factors we need to consider to make sure the ride is very enjoyable. And we've also determined our stakeholders' needs and how we're going to achieve their goals.
Work to do in the second half of the semester. So by the time we return to in-person classes, we'll know which of our 3 variations we want to model, how to build it, and what materials we need. So we can gather our building components, make our model, and we can test it to see how it behaves in comparison to our theoretical models. Afterwards, we can modify our model and improve upon it for Scary Rides Incorporated.
So what kind of paths are we considering for our roller coaster? The most obvious solution would be a cycloid curve. This is the calculus solution to the problem of quickest descent, and will get the riders from the top of the curve to the bottom of the curve in the shortest amount of time. This will be very fast and also very fun. So this is the curve shown in the picture on the left. A circle and a 6-degree polynomial shape are also top contenders. They will also be quite quick. And a circle, you could do a loop-de-loop, and the 6-degree polynomial would be a very steep drop, which could increase the fun factor of the ride. Anything really that generates large accelerations increases the G-force felt by the riders, which increases adrenaline, and this makes the ride more fun. There's also a psychology aspect. So the colors, the theme, the location of the ride can provide just the right amount of fear to make the ride a little bit more fun. We want to avoid a straight path, as this is quite slow, and any sharp high-speed turns. So if you're coming out of a big drop, you don't want to turn very suddenly, as this can cause the head to accelerate relative to the neck and the rest of the body, and this can cause neck and spine injuries. And anything that exposes the riders to 6 Gs or higher, so 6 times the acceleration due to gravity or more for long times, is not very safe. You can pass out. So we definitely want to avoid that, but it's quite difficult to achieve, so it's not expected to be a problem.
To build a scale model of the roller coaster, the most accurate way to model it would be by 3D printing all the parts and attaching them. So for materials, we will need lots of PLA, which is a renewable thermoplastic, some popsicle sticks for support, glue and zip ties for connecting parts, and maybe some small bearings for wheels on the cart. As well, we will need access to the 3D printer to print all the parts. Steel construction would be the most beneficial because it's more load bearing and it's able to have more complex designs in ways wooden roller coasters can't. For example, steel coasters can have upside down portions and sharper corners, as well are generally taller, faster, smoother, and more thrilling. Also, having steel track would require less maintenance. While initially thinking that wooden roller coasters would be more environmentally sustainable, steel is actually the better option because wood is essentially a single-use material, and once it becomes unusable, it's either burnt or goes into a landfill. This affects the greenhouse gas emissions, and steel is one of the most recyclable materials in the world.
An important aspect of the roller coaster project is being able to set goals and verify their achievement. We have identified 5 main functional requirements that the roller coaster must satisfy for the project to be considered a success. First, at the core of the project is the drop, where riders must reach the bottom in an optimal time. Ensuring that our drop follows a perfect cycloid curve, as well as reducing friction and energy stored in rolling motion, will help achieve this main goal. We can verify our success by using simulation and mathematical analysis to ensure that our curve is traveled optimally. We can also test various other drop shapes to conclude that the cycloid is best. The ride must also have exciting features, which are tough to verify, as this is the most subjective aspect of the roller coaster. We must use our best judgment as people who enjoy riding roller coasters to verify that the ride will be fun and thrilling for its passengers. The final 3 aspects of the ride require it to be financially feasible, safe, and structurally sound. A financial analysis can be performed, including material costs, labor costs, and a projected increase in revenue for the park to analyze if the ride is worth installing. The ride's safety and structural integrity can be verified using G-force analysis at sharp turns and drops, and structural analysis on the columns and beams to ensure that the ride is stable. Verifying all of these requirements will guarantee the success of our roller coaster.